Hello, climate fans. Patrick Love here again. This is lecture 4 of my climate science course. So we are going to start out now in this lecture with the relevant question about is the Earth warming? So the question, of course, is it getting warmer? And on the surface, that seems like an easier question to pose and answer because you just say, oh, year over year, is it getting warmer? It turns out that's not particularly easy to measure, but we'll get into the details of that. But it does seem like a question we can answer yes to. What may be a little harder question is how significant is this warming relative to past climate history? After all, the Earth has had a long history. It's 4.6 billion years old. And so what kind of warming have we had in the past? In other words, is this significant warming? So we're going to take a look at paleoclimate. Before we start that, let's just ask a simple question about what are we saying, what is warming? What part of the Earth is warming? So we're typically here talking about the surface of the Earth, what we experience. That is the near surface atmosphere, the troposphere, and the oceans, the land, and the oceans, right? Because the oceans are near surface, right? So the top mixed layer of the ocean, which is, let's say 1,000 meters, we can get measurements of that and see if that's warming. So that's what we want to do. And so that's what we say is warming anyways. So what we would like to start out with is looking back in history. So we have a beginning part of this section, this particular lecture 4, is about paleoclimate, the old climate, and trying to find out what we know about it, right? What we've learned about the old climate. We have two ways to do this. We can analyze information from ice cores drilled in Antarctica, and we can analyze information from drilling deep sea sediments, taking cores from the deep oceans, where we're able to analyze information from the shells of ancient critters who lived in the oceans and absorbed some of the water and used it to make shells. And we are going to look at the results from both of those different kinds of analyses. We have to know a little bit about oxygen isotopes and hydrogen isotopes to do this, because we're going to use a well-known physical science trick called isotope fractionation. Basically, that trick is based on the idea that if you have different isotopes of the same element, they behave chemically the same, but in certain physical processes like evaporation, condensation, they behave differently because they weigh different amounts, right? So let's take oxygen as an example. Oxygen actually has 3 isotopes. So what you should say is, or what you should know is, that the element oxygen has 8 protons and 8 electrons, and that stays the same. That's what makes oxygen oxygen. And its 8 protons and electrons, particularly electrons, determine its chemistry. So its ability to interact with other elements and so on and so forth, its chemical processes are essentially determined by its charge, which is 8 protons. And of course, the 8 electrons make it a neutral atom, but basically they occupy certain orbital states, which help determine its chemical interactions. However, different elements can have different numbers of neutrons in the nucleus. So the most common form of oxygen is oxygen-16, which has 8 protons and 8 neutrons. However, there's an oxygen-17, which is very rare, and there is an oxygen-18, which has 8 protons and 10 neutrons. And because oxygen-18 is heavier, it behaves slightly differently in processes like evaporation and condensation. Something similar is true of hydrogen. Hydrogen has three isotopes. Basically, the very simple isotope called protium, which is one proton and one electron. And then there's deuterium, a proton, a neutron, and one electron. And there's even tritium, which is even smaller amount. But if you look at what it typically used in these kind of isotope analyses, they would use protium and deuterium to see what they could measure in terms of fractionation. So when we mean by fractionation, we mean there's a different fraction of, in other words, a different ratio of the isotopes, different proportion of the different isotopes of the same element, depending on some physical property of a process. For example, the temperature of it that's driving a process like evaporation. So to illustrate that a little more, we're going to go to a little sketch I have made here. Let's start at the top with the warmer climate, right? And in the warmer climate, what we have is we have the ocean here, which is made up of water. It has salt in it too, but let's just stay with the water for a second. It has H2O in it, right? And some of the O in the H2O is oxygen 18, and some of the O in the H2O is oxygen 16. We also have what are called foraminifera. These are little animals. There are benthic ones, which means they are down near the ocean floor, and there are also plankton foraminifera that float in the water up near the surface. They're little floaties, if you want to think of them that way. These are little animals that have calcium carbonate shells. Calcium carbonate is Ca calcium, C for carbon, and 3 oxygen atoms. And of course, those oxygen atoms can be either oxygen 18 or oxygen 16. We would expect them to have about the ratio that we universally have, right? We might expect that, but what's going to happen is they're going to be slightly different. So what happens in a warm climate? Well, in a warm climate, some of the water evaporates, and because the oxygen 16 atoms are bouncing around a little more in the water, there is a tendency for the cloud to form with a higher proportion of 16 to 18 than the water itself. Does that make sense? Because the 16s are lighter, they're basically going to evaporate easier. Then when the cloud, let's say, gets pushed to the north and eventually rains, it rains out predominantly 16. If the climate's warm enough, the 16 ends up back in the water, right? And so not a huge change in the ratio of 16 to 18 in the water. The shells, the foraminifera shells that are formed, if the water is warm, the 16's moving around more than the 18. The shells basically are crystals, and in order to capture an atom, in order to capture an oxygen atom, the crystal has to kind of like grab it and pull it in chemically. And it basically is a chemical reaction. And the 16s are more easily absorbed. I'm sorry, the 18s are more easily absorbed because they don't move around as much. But if the water's fairly warm, the differences are a little smaller. In a colder climate, basically you're going to get enhancement of the separation of these two isotopes. The 16 will evaporate easier, so you go down to the bottom page. The 16 will evaporate easier and end up in the cloud and then go rain on the land, let's say, or snow on the land. But because the land is colder and if it moves north and ends up in an area that's even colder, it's going to form ice. And the ice is going to be rich in oxygen 16 relative to the expected ratio, right? Because it evaporated easier and it rained out. Along the way, if there was 18 that evaporated, when it rains, it might rain out. And so what gets far enough north to make snow is going to be 16 enriched. Basically, then the water is going to be 16 depleted because it's not getting back into the ocean. It's being caught up in the ice. With the foraminifera shells, because the water's colder, they're going to grab more of the 18 out of the cold water. Remember, 18's composition is now enhanced because there's less 16, because the 16 left and it's being captured in ice. And the foraminifera have an easier time capturing the 18 because it doesn't jiggle around as much because it's heavier in the water. So basically, the foraminifera end up in a colder climate, oxygen 18 enhanced, right? The foraminifera sink to the bottom and end up as sediment, and the ice piles up on shore as glacial ice. The bottom line is, if you find more oxygen 18 relative to 16 in calcium carbonate marine minerals in the sediment, that means they were formed in colder temperatures. If you find more 18 relative to 16, you also means there's more glaciation. In other words, implies that there's more ice being formed because the water is depleted in 16, it had to go someplace. And less 18 relative to 16 in glacial ice results from a colder polar temperature, right? So this means that we can set up a temperature scale using these isotope measurements. And that's what we do. And in this next drawing, I've referenced the authors down below. In 2008, this was published. This is actually the result of a oxygen isotope analysis. It shows sea level on the left and temperature on the right, and the temperature is relative. So the x-axis scale is time before the present, with the present being the 0, 0 to the left bottom is the present time, and the 0 there for the y-axis should be read as the present sea level height. Now, a little bit of confusion here. The way the data were presented in the paper, they had positive sea level height. So you notice sea level goes up to 120. That should actually be, in a sense, it should actually be negative. It's basically saying that if you go back a number of years, sea level is 120 feet lower than it is today. Okay, so going up means lower than today. It's a little confusing. Temperature scale is negative, it's colder at the bottom and warmer at the top. So what you see on this curve is if you follow the blue line is the surface temperature of the Earth, roughly speaking, right? So basically the surface temperature over here at the present time is at 0. So these measurements are not an absolute temperature. These are going to be relative temperatures. So they're just taking 0 as today's temperature, which we know is about 60 degrees Fahrenheit. And so now we come down, this scale on the right is in Fahrenheit. And basically we come down the temperature curve and find out that if we go back before the present, some 20,000 or 18,000 years, we get down to almost 12 degrees Fahrenheit colder. There is this period here where it's cold, and then we have another short warm period where it gets as warm or slightly warmer than today, and so on. You follow this blue curve. What you see are 4 to 5 warm periods, and which are fairly short, something like 10, 15,000 years, maybe 20,000 years, and some long cold periods which vary in temperature between the warm periods. along this time frame. Also shown are the relative sea level. So again, today is 0, and 120 means that during that cold period at 25,000 years ago, sea level was about 120 foot lower. And you can see that during the cold periods, sea level was somewhere between 100 and 125 feet lower with lots of variation, right? Again, the positive scale means lower on sea level, and that's in feet, right? Now, this says the Cenozoic Ice Age. The Cenozoic is the time we're in today. The reason it says ice age merely refers to the fact that there's ice on the planet, right? In an ice age, there are glacials and interglacials, glacial periods and interglacial periods. The cold periods between these warm peaks are called glacial periods. That's when the ice expands and the sea level goes down, right? The warm periods are where the ice melts and sea level goes up towards the present, which is actually down on the graph. Sorry about that. And the Earth gets warmer. And you can see that the variation is something like, 10 degrees Fahrenheit, 10 to 12 degrees Fahrenheit. And these warm periods are 10 or 20,000 years. The cold periods in between them are longer. The time between warm periods is roughly 100,000 years. So you can kind of get a feel for these. And if you went, this graph, I only plotted 500,000 years of data. But if you were to go back 3 million years, you would see this kind of back and forth between glacial and interglacial periods, right? So you just keep seeing more of these peaks and valleys. And admittedly, they're very noisy, but you do get these peaks and valleys. Now, what's causing these? That's a great question. What's causing these are orbital variations. So basically, the orbital variations, there are 3 kinds of them. One is it turns out the Earth's orbit is nearly circular, but at time it actually stretches a little bit and becomes more elliptical and circular with about 100,000 year period. That's called the eccentricity of the orbit. The variation in the eccentricity is the 100,000 year variation. There is a variation in the tilt of the Earth, the axial tilt of the Earth, from something like 22 degrees to 24.5 degrees. And there also is a precession of the Earth. Oh, by the way, the axial tilt has a period of 40,000 years. Oh, by the way, the axial tilt has a period, I think, of about 40,000 years, and that's right, 40,000 years. And then the third one is the precession of the Earth's orbit. The orbit actually precesses around the sun. There's also precession of the axes of the Earth. That's important. And there's a precession of the orbit around the sun. That is, the orbit kind of swings around the sun, and the axis tilts. Axis sort of spins like a top. So it's sort of a top that's kind of constantly rolling over. Those precession effects are kind of 20,000 years. Now, if you think about, these things all happen at once, of course. And as a consequence, what happens is during the last 3 million years or so, the Earth has been largely in an ice age, right? During that time. I showed you the last 500,000 years of that ice age, the Cenozoic Ice Age. And in glaciers and interglacials periods are being driven by the amount of sunlight roughly that falls around 60 degrees north in the northern hemisphere. Because what really matters is when it snows in the winter, does that snow make it through the summer so that it stays on the ground? And if it does, then you get snow piling on top of snow, and you get an albedo effect. You get a reflective surface in the north, which basically reflects more energy, thus making the Earth even cooler. That's a feedback effect. We'll talk more later about feedback effects. But basically, if that snow survives the summer, because the sunlight in the northern hemisphere where there's lots of land, if the sunlight is less, partly due to some combination of these orbital effects, then you get to build up ice from year to year. And you start to cover more and more area with ice and snow, and you get more and more reflectivity. The Earth's albedo goes up, and the Earth gets colder. And you might say, why doesn't this run away completely? And the answer is, of course, because the orbit and all these things change again, and gradually you get some more sunlight in the northern hemisphere, which tends to melt more ice and reduce the albedo. And that's where you get into the warm periods. Okay, and so there was a famous Serbian mathematician. His name is spelled at the top, Milankovic, who very patiently sat down. You can imagine this is a difficult thing to do. Patiently sat down and figured out what the amount of sunlight falling on the Earth at 60 degrees north, given the orbital parameters of the Earth, would be. And that variation, total amount of sunlight, matched very closely, matched the relative pattern of these effects. Now, there are other effects going on during these glacial interglacial periods, and let me show you that in the next slide. I want to just back up a minute. Let me back up a minute and just say, this is based on oxygen isotopes from, I believe these are taken from benthic foraminifera. So now we're going to go to an ice core. This is ice core data. The ice core is taken from in the Antarctic. It's called the Vostok. And this data was published in 1999. These are my graphs of the data that's in these papers. And there's two axes on this graph. On the left is an axis that is parts per million of CO2. Remember, the unit parts per million means we're counting the number of CO2 molecules relative to the number of air molecules. So this says that when you go through these periods of glacial and interglacial periods of time, the CO2 is varying from something like, let's say, 180 to maybe 280 parts per million. And that is represented by the black squares, right? On the right-hand side is temperature in Fahrenheit. And again, you see a variation from something like a total variation of about 10 degrees Fahrenheit from the glacial periods to the interglacial periods, right? The warm periods. You'll notice that these curves look a lot like, if I can go back, a lot like this period. Unfortunately, this one's a little confused because I've got the sea level on there, but you can kind of tell that they're very similar periods, measured in a very different way. So one's from ice cores, one's from foraminifera, one's using oxygen isotopes, this is using hydrogen isotopes. As a consequence, we have some considerable confidence in these things. You might say, how are we measuring CO2 in these ice cores, right? You know how we're measuring ice. Ice is frozen H2O. You can use the hydrogen isotopes or the oxygen isotopes in the ice to measure the fractionation, and from the fractionation, you can infer the temperature. But how are we measuring CO2? Well, if you look at one of these cores, this is one of them held up to the sun behind it in Antarctica. And you can see all the air bubbles in there. Isn't that a beautiful thing? And you can actually go in and capture the gas that's entombed in those air bubbles, and sort out the CO2 and ask what the ppm of CO2 is, basically count the CO2 molecules, and figure out what the CO2 concentration is. And you know the age of this just by looking at the layers of ice. The layers aren't as obvious in this picture, but there are layers of ice you can count your way through to figure out the age of, to figure out where you are in the history. Now let me show you this is just the same Vostok data that I had before, but it is drawn here with just the last 80,000 years, so as to expand where we have been recently. So just to call your attention to a couple of ideas here. So the Earth has warmed up, 20,000 years ago was pretty doggone cold, maybe 10 degrees Fahrenheit colder on the Earth on average. So that means it's really cold. And in the last 10,000 years, we've been in a warm period, right? This warm period is called the Holocene. We've been in the Holocene for about 10,000 years. It's in the Holocene where, for most of that time, up until very recently, CO2 was somewhere around 250 to 280, depending on when you measured it, let's say. Back in the previous period, CO2 was down around 180, 190, 200, 210, that kind of range, right? And we might say that a lot has happened in the last 11,000 or 10,000 years in terms of us on Earth. But basically, the Earth has been in this ice age for maybe 3 million years. Glacial and interglacial sea level has varied by 100 plus feet. The temperature's varied by 10 degrees Fahrenheit. The human population and culture, technologies have expanded dramatically during this most recent Holocene. We've been around, well, if you want to think of hominids, our ancestors, they've been around maybe 1 million to 2 million years. We seem to be finding more and more older hominids all the time. And Homo sapiens, the more modern form of us, of our species, have been around for a couple 100,000 years, but with fairly low population. So in the last, our population has taken off in the last couple 100 years. So if we look at sort of our history, if you think of our history as a book, and you think of this story that I just told you about our measurements of past temperature, basically, let's say a couple 100,000 years ago. So let's think of this book that every page in the book is a couple 100 years, right? So page 1, 200,000 years ago, we were evolving from various ancestors of hominids. 100,000 years ago, there was a large exodus out of Africa into the Mesopotamian region. That would be on page 500. On page 750, we demonstrated language some 50,000 years ago. Farming started on page 930. The first city, Rome, the first city with 1 million people was about 14,000 years ago. Rome had 1 million people in it 2,000 years ago, around page 990. And in the last 200 years, on the last page, page 999, we started using fossil fuels for energy, cars, up until the last page, we were basically either riding on an animal or walking to get places. And there weren't any appliances, really. We were doing things pretty much on our own. This is what's happened to the world's population in the last 10,000 years of the Holocene. We were probably about 4 million, this is hard to estimate, but maybe around 4 million people back in 10,000 BC. The average growth rate was, maybe 1,700 per year. We might have been a couple 100 million people in year zero, and we have gone up pretty dramatically. So in 1800, we were approaching 1 billion. We now tend to go up 1 billion every 12, 15 years, 20 years, depending on the actual time frame. So we have jumped up dramatically in the last 400 or 500 years in population. And we have lived in a good time, and we've expanded in a good time for humans, right? I should say something about this Holocene that we're in, this warm period that we're in. The Earth's orbit is pretty circular at the moment, and the circularity tends to, in a sense, amplify the other two orbital variations. So because the Earth's orbit is fairly circular, we do not expect a return to a cold period for a while, right? That a while might be thousands of years, certainly tens of thousands of years. So we don't need to worry about that right away, because the orbital dynamics suggest that we are not going to get real cold soon. Okay, so let's go back to a geologic time scale again, just to put this in a context. I want to show you one more example, a paleo example of temperature variation. So remember, if you look at this, you see the Cenozoic on the right-hand scale, right? The right-hand scale has the Cenozoic, the Mesozoic, and the Paleozoic, very creatively named, right? The Paleozoic is old times, Mesozoic is middle times, and Cenozoic is now times, if you want to think about it that way. You notice the Paleozoic goes back to about 570 million years, right? And you can think of that as the time in which multicellular life emerged on the Earth. Before 570 million years, it's kind of remarkable. The Earth has been around 4.6 or 7 billion years. But for 4 billion of those years, the Earth had nothing more complicated than very simple single-celled organisms. But it may be as complicated as bacteria, things like that, but not much. And then around the Cambrian, you get this explosion of multicellular life and a lot of interesting changes. So if you think of the Paleozoic, your favorite animal of the Paleozoic were tribolites. They got wiped out in one of these mass extinctions. During the Mesozoic, your favorite animal is probably the dinosaur. And during the Cenozoic, if you're not picking us, you're picking something warm and fuzzy like a rabbit or something as your favorite animal. But certainly some kind of mammal during the Cenozoic. So basically, during the little blue dots on the right-hand scale are the 5 major mass extinctions, which wiped out something like 70 or 80% of the species on the Earth at that time, sometimes as high as 90% of the species on the Earth. These were large climate changes, typically, that happened suddenly. Of course, we all know the dinosaurs had a couple of climate change effects, one due to the impact of an asteroid, which hit down by Mexico, wiping out the dinosaurs. But I want to pay attention to the PETM on the right, the PETM. That was the Paleocene-Eocene thermal maximum. There was a period of time there where there was large volcanic, they believe a large volcanic eruption put a lot of carbon dioxide in the air and caused a large warming. And I will show that to you. Let me just back up 1 second. If you go back 3 million years, if you look over at the epochs, right? I said the recent one is the Holocene, then the Pleistocene, and the Pliocene, right? You're seeing that in the drawing here, right? The Cenozoic Ice Age goes back into the Pliocene, right? And that's where you get these orbital variations which cause the glacial interglacial periods. If you go back to this boundary between the Eocene and the Paleocene, we have this thing called the Paleocene-Eocene thermal maximum. The next graph shows the isotope excursions that correspond to this. So basically in the upper Paleocene, you get this big jump in both planktonic isotope ratios. So you get a big thermal spike here. This is carbon isotopes and oxygen isotopes. You notice how they correspond. And you get this very large increase in temperature, right? And we believe this is because we've dumped a lot of CO2 in the atmosphere. The important part of this study, which has been going on, this goes back, now we're back at a time in this boundary in the Paleocene-Eocene, where even the continents are not in the same place. You know that continents move around. They basically move around kind of, well, today they move around about as fast as your fingernails grow. But in those days, they moved around a little faster, but they were in different places. And as a consequence, it's difficult to exactly know how the Earth's circulation was in those days. When you go back and measure these things back, you know, these isotope excursions too far back in history, it's hard to know exactly how the climate worked. But the bottom line is it took a long time for the Earth to cool off, something like 170,000 years before things returned to normal. There was a significant drop early over maybe 30 or 40,000 years, but then a slow, steady drop over a long period of time, which says the natural processes for removing carbon from the atmosphere are slow. And we're going to get into that. You might say, well, you might say, you know, the Earth does a pretty good job of managing key variables, and won't Mother Nature take care of some of these things? Well, she does, but if I can use the feminine pronoun there, but Mother Nature does it sometimes slowly compared to the lifetime of a human, for example. So 100,000 years is a long time in human history, as we've just reviewed when we were looking at the Holocene, right? So this is an important event for studying how long the Earth would take care of excess carbon put into the atmosphere. This is a proxy reconstruction. So now we're going back just 2,000 years. This is a reconstruction, actually it's done by several groups. All the different colors are different groups of people. It's very noisy data, but this is data that looks at what the temperature has been using. Again, it's kind of zeroed at a particular range and then relative temperature, using data like tree rings and various kinds of other sediment, plant debris and stuff like this of all different types. It's very noisy data. It's hard to say a lot from it. You do sort of see roughly the medieval warm period and the Little Ice Age. But typically what it says is, if you look at 2016, that little hash, that little mark up there, that's our current temperature. It's about a point, in 2016, it was about a 0.7 degree increase over, say, a temperature in the 1800s. Basically sort of says, if you go back 2,000 years, while we can't really get a very accurate temperature number, we can see that the numbers weren't as big as the recent excursion. That's about all you can say from these reconstructed temperatures, even though a lot of work goes into these. Okay. So we are going to move on to direct measurements of the temperature. And so these measurements are done with instruments and of various sorts. And we're going to talk a little bit about these. So to the question, is it warming? What we've just done is reviewed the context in which these measurements are made. And before we dive right into the measurements, I want to say a few words just about what is temperature. So this is an example of a thermometer. It's a pretty crazy one. And I constructed this just to illustrate what temperature is about. You'll notice we've got a little human observer inside a room that's 10 foot on all sides. In other words, the area of the floor is 10 foot by 10 foot, and the height of the room is 10 foot. There's a volume above the room that's drawn to a vacuum, and there is a piston on this. The room is basically, the ceiling is basically a piston, so it's sealed along the edges. The piston weighs 211,000 pounds, and there is one atmosphere in the room that is the same atmospheric pressure you have at sea level of 14.7 pounds per square inch. The room's at 32 degrees, and we can heat and cool the room to change the temperature. All right, and that's the experiment we're going to run. And basically what this frictionless piston does is it moves up and down depending on the temperature. The 10 foot is based on 32 degrees, and basically the room is full of 1,300 moles of atmosphere. A mole, as you might remember from your high school chemistry, is 6.02 times 10 to the 23rd molecules. And the question you can ask is, why is the piston suspended in the room? What's holding it up? And obviously it's the pressure of the gas in the room that's holding it up. And the pressure of the gas comes from, and I've illustrated this with some very unrealistic motions of molecules drawn as arrows. Basically, molecules in the gas are banging up against the piston, thereby keeping it up there. They transfer their energy to the piston, and they run around the room, bouncing off our observer and the walls and so on and so forth. And in fact, if we raise the temperature of the room by a degree, the piston will move up about 1/2 inch, right? So basically that's in the sense in which it's a thermometer. In fact, the temperature in the room is directly proportional to the average kinetic energy of the molecules in the room, which, as you might remember, is their mass times their velocity squared. But the main point is that the temperature is a measure of the energy in the room. And that's the main point that I want to make with this. The paths shown here are not realistic, the molecular paths. A nitrogen molecule, which is mostly what the air is made up with, is moving around in this room at 1,100 miles per hour. And it only goes about 100 nitrogen molecule diameters before it runs into another molecule, which is like 0.00000001 inch before, or meter, sorry, 1 meter before it runs into another molecule. So these long paths I've drawn aren't very realistic. At any rate, the main message is simple. Temperature is about total energy in the room. That motivates this measurement. This is a very famous curve. You probably see this in the newspaper and various other places. This is called the land and sea surface temperature measurements, sometimes called instrumental measurements. First done by Hansen and others at the Goddard Space Flight Center. Has been happening for many, they've been doing this measurement for decades. There are now about 8 groups around the world that make these kind of analyses. They all roughly agree with slightly different dots in slightly different positions. I stuck with the Hansen measurement. You can see that our current numbers for, say, 2019 would be around 58.9 degrees or 59 degrees Fahrenheit. They use a mid-century baseline of 57.2 to talk about these, but I put it on the absolute scale so you could see the numbers. you could see from 1880 on, you have a fairly flat but very slow rise through a period of time. And then from about 1970 on, we've had quite a steady increase, with periods where it's been not moving much, but then it takes off again. So, you know, really when you're thinking about climate and parameters, we should be thinking about averaging over 20 years or something. Now, these are annual averages. And when this is the kind of thing that a lot of scientists sort of cringe at when think about what goes into every one of these dots. So there are something like 10 or 11,000 land stations that measure temperature that go into these dots. They're all over the world. They're, of course, denser in high population areas, so you can't just average them. You have to kind of put on a grid, basically even out the measurements so you don't overweight one area relative to another. If you have 10 measurements in New York City, you don't want to weight that temperature by 10 times relative to one measurement close to the North Pole, right? So you have to do some method of statistical smoothing to figure out how to not overweight one area relative to another. And then you're going to take measurements from the ocean. Now today, in more recent times, you have much better measurements of surface ocean water. But in the old days, way back in the 1800s and early 19s, they used to take a bucket of water from the ocean, bring it up on the ship deck and measure it. For a while, they had water circulating through the engines and they could measure the intake water temperature, which was a common thing to do. Today, we have floats in the ocean that measure temperature. So all these different methods have to be cross-calibrated. And so for every dot on this curve, there is an awful lot of spatial analysis. There is an attempt to sometimes take out the urban heat island effect. In other words, you can get bias if measurements in cities are warmer than measurements on their outskirts. There's an awful lot that goes into this, right? And for that reason, these curves have been hotly debated for years. People will say, oh, and you can imagine Hansen went before Congress in the 80s and talked about the increase in temperature. If you were in the 80s, you could decide whether you would have the courage to do that. Of course, he knew a lot more than just these measurements. He knew what was going on with CO2, and he had a very good understanding of why CO2 would influence the temperature of the Earth. But nonetheless, today, I think it takes a lot less courage to say the temperature is going up, even though it's a complicated measurement to complicated method to construct the measurements. The next graph talks about shows all the different people who do these analyses on a monthly basis. This is just from 2012 to 2018. We have taken a baseline out, so it's not as steep as shown on the previous data. Doesn't have much of 2019 in it. Doesn't have any of 2019 in it yet. But basically, what I wanted to show here is how well the different groups. There's NASA. The NASA group is the not the light blue, but kind of a dark. It's hard to see. It's kind of a dark blue. That's the NASA Goddard group that was on the that was for the whole previous graph. But you can see that there are many different groups that do this, and they all tend to agree more or less, even by the month, with some noise of maybe a tenth of a degree or so. All right. Now, because let me go back here. These are annual averages, right? This is monthly, and this is by area. So you should not believe, so this is the change in temperature, I believe from the baseline till today. So that baseline I said, let's go back and look, oops, wrong way. I'm always going the wrong way. The baseline is 57.2. So this is the change in temperature by place on the Earth, right? So what you see is the temperature has changed dramatically differently from place to place on the Earth. So that global average is actually not showing us what's really going on with this temperature change. However, the reason that we're motivated to do this is basically because we're saying that that dot is representing something about the total energy that's in the surface layers of the Earth, the lower troposphere and the oceans, the top level of the oceans. And so we're saying that's a measurement of how that surface layer is, the amount of energy it has in it, right? That's the motivation for this measurement. But you can see that it varies a lot depending on where you are. This is one kind of drawing that sort of shows the quantification. This is another drawing. And these emphasize a very interesting phenomenon. And that is that the pole, the North Pole in particular, is warming a lot faster than the rest of the Earth. Now, the rest of the Earth is warming. There's no question about it. But the northern latitudes, at least at the moment, are warming more. You also see that there are areas that are cooler. For example, off the coast of Greenland, we have in the North Atlantic, we have a cooler area. Some of that is caused from melting runoff from Greenland. And you might ask, well, why are the northern areas warming? And generally we believe there are two reasons that have been proposed, and the climate models that we have for the Earth seem to support these reasons. One is that since this is a satellite picture since 1979. It shows that 40% of the polar ice cap has melted away in the summer. That is, that red line is where the boundaries of the polar ice cap would have been in 1979. This is where it is today. You'll notice Greenland sticks out there, as the ice on Greenland is a grayer ice. And so you get less albedo, and in that region, that lower albedo, in other words, the albedo changes from ice, which is maybe 80% reflectivity, to ocean, which is less than 20% reflectivity, a huge change in albedo, which tends to mean that area of the ocean is warming because it is absorbing a lot more energy that was previously reflected by the ice. The other reason is that we seem to be seeing, and this goes back to what we learned about the 3-cell model, between the Ferrel cell and the polar cell, we know there's the jet stream. And the jet stream, the strength of the jet stream is related to the contrast in temperature between the cold air, sometimes called the polar vortex, and the warmer air in the Ferrel cell. Well, if you have some decrease in that temperature contrast, you can get the jet stream that goes weaker. And when it goes weaker, you get these waves in it. Now, you get these waves in it even when it's strong, but these waves tend to move more slowly. And basically, you get these bigger waves, higher amplitude, moving slowly. And what happens is you get these cold air excursions into the mid-latitudes. And as the cold air comes down, warm air goes up. And so you get kind of, if you look at this picture, you get some warm air incorporation into the polar region and cold air incorporation into the mid-latitude region. Some kind of mixing, if you think of it that way. And because the jet stream has become weaker. Now, this is preliminary understanding, and a lot more work is going to go into this in the near future. But the idea is that this may be partly responsible. This, together with the albedo effect, may be what's driving some of the variation by region of the warming of the Earth. Okay, this is lecture 4, Is It Warming? So what we're going to say as a conclusion here is that in contrast to our past history, CO2 has gone up to, let's say, 411 parts per million from a range during the glacial interglacial period of the Cenozoic Ice Age from 180 to 280, let's say. And that we have seen a temperature change of something like 2 degrees Fahrenheit since the 1800s, as measured directly with instruments, right? And that should be compared with about a 10-degree Fahrenheit change when we went from glacial to interglacial. But one thing we need to remember is that 2 degrees Fahrenheit change is on top of a warm period. So basically, we're sitting on top of a glacial interglacial warm period called the Holocene, the last 10,000 years, and we're rising above that warm period into a region that we haven't been before, and into a region of CO2 range that we haven't been before, right? And so those are interesting, interesting differences. One last point I did not make, and I'm going to stream back quickly to make, and that is that if you look at, sorry, I want to find this graph. If you look here, we're saying the CO2 is varying glacial, interglacial like this as the temperature goes up and down, right? However, what we believe is happening here is that not the whole temperature range, the whole 10-degree Fahrenheit temperature range, is not driven alone by the Milankovitch solar intensity at 60-degree north theory, right? You'll notice that CO2, it looks like, remember, time is increasing to the right. I'm sorry, to the left. It looks like the CO2 is lagging the temperature change. So it looks like the temperature is starting to change and the CO2 then follows, right? And that might make some sense. It says that as the Earth gets colder, as the oceans get colder, they can capture more gas and they capture CO2 out of the air. That's a basic, as you warm up liquids, they get rid of gas, and because it's harder for them to capture gas, it's less soluble. Gas is less soluble when the liquid is at a higher temperature. So it looks in these graphs like CO2 is following down the effect of the solar intensity at 60 degrees north, which then causes an albedo change, a reflectivity change, which then makes the Earth colder. But we also believe that the fall in CO2 also contributes to the cooling of the Earth, even if it's being triggered by the orbital cycles. Less CO2 in the atmosphere will give us a smaller greenhouse effect. Similar on the rise. The rise might be triggered by the orbital effect, but the rise in CO2 to 280 parts per million is going to also enhance the warming. So think of this as the triggering of these glacial interglacial cycles is most probably due to the solar intensity at 60 degrees north, causing ice changes, causing albedo changes. But when that happens, CO2 is either being released or absorbed from the oceans, thereby causing cooling or warming that's in synchrony with the temperature change from the albedo effect. And without getting into the models, this basically needs to go together, otherwise you don't get as large a temperature effect. And there are still some questions about the details of whether these two things fit together to have the temperature effect and where the CO2 is coming from and all that kind of stuff. But it's clearly there, right? And so I wanted to emphasize that before we end the lecture. So on that note, we will end our lecture. I want to stop sharing. In lecture 5, we are going to talk about other confirmations that the Earth is warming. So it isn't, the fact that the Earth is warming, there's other things you would predict should happen. And we're going to look at measurements of those other things. So thanks for being here, and looking forward to seeing you in lecture 5.